Alright, hello everyone. It's the next installment of the Physics 216 videos. What we've been talking about recently is planetary orbits. So these are, for example, we assume that we have a very massive sun which remains stationary, and then it exerts a gravitational force on, say, Earth. And so what kind of orbit could the Earth take around the sun? And what we found out is that in general, the orbit is elliptical. Um, and then we thought about it more carefully and we said, well, actually, there's conditions under which that orbit is bound or unbound, and that was related to whether the total energy of the system was positive and negative. And so it was kind of an interesting problem where we were thinking about things on astronomical scales. What I want to do today is I want to talk about Rutherford scattering. And so, what is Rutherford scattering? We're going to imagine that we take a particle of charge Q and mass m, and that particle is incident on a fixed, i.e. a very heavy particle of charge Q. And so for the purposes of this topic, let's suppose that both charges are positive charges. And so the picture is going to look like this. We're going to have our heavy fixed charge of capital Q, and say mass big M is really big, so our other particle is going to be mass little m, and big M is much bigger than that. And what we're going to do is we're going to fire at this charged particle, capital Q, another particle, and this other particle is going to be charged little q and mass little m. So over here we have mass little m and charge little q. And what it's going to do is when it's far away, there's going to be some kind of force between these charged particles, but it's going to be very weak. Okay, so there'll be a Coulomb repulsion, but when the distance is far, that is pretty weak. And so our charge little q, if it started in this horizontal path, it will just remain approximately in this horizontal path until it gets close enough that this Coulomb repulsion gets substantial, and then its path is going to be deflected. And it will be deflected in such a way that maybe it does something like this. And then once again, when it gets far enough away from big Q, it will be moving in a straight line. Notice that I didn't have these particles exactly in line. They were offset by some distance. That distance is called b, and it's known as the impact parameter. So before we go too far, this experiment was actually done a long time ago by Rutherford, if you can believe it. And what he did is he was firing what are known as alpha particles. So an alpha particle is a helium nucleus. So you take helium, which is 2 protons and 2 neutrons. So it has a mass of 4 nucleons, and it has 2 electrons. So an alpha particle is you strip off the electrons, and so you have a charge of +2, and so this is an alpha particle. And what they were doing is they were firing these alpha particles at a very thin gold foil. And if the gold, which is very, very thin, is made up of most of the mass being concentrated in the nuclei of the gold, then there's a bunch of empty space between them, and that would lead to some kind of characteristic scattering pattern. And so they were looking for how these alpha particles scatter from the gold foil. Okay. Anyways, what we could do is we could say, at some point in time, maybe the position of our alpha particle relative to the gold nucleus is here, and there's some radius r, and here is some angle theta. And what we're going to do is we're going to say, well, let's suppose that we define, let's extrapolate a line back from the straight line after our particle has scattered. And so we extend that back. And what we're interested in is this scattering angle theta. Let's say theta s is our scattering angle. And so the question that we want to answer today is, if we know things like the mass of our alpha particle and its charge and the charge of our gold nucleus, and for example, for a particular impact parameter b, could we calculate the scattering angle theta s? So the question is, what is the scattering angle theta s? Okay, well, what we would do is we'd say, well, the force on our alpha particle q is just the Coulomb force, 1 over 4 pi epsilon naught, and then it's the product of charges divided by the square of the distance, and that is going to be this is be a repulsive force, so it's going to be in the direction of r hat, where r hat would be along this radial line. Okay. So in that case, what we would say is, by Newton's second law, it must be the case. Well, let's write this in terms. Let's write 1 over 4 pi epsilon naught as Coulomb's constant, Ke. And so this is Q over r squared, r hat. Okay, so then Newton's second law says that mass times acceleration, which is mr double dot, is just equal to that net force, and there's only one force on our alpha particle, like so, where the position vector r is just equal to r hat. And then you begin to look at this and you say, well, wait a minute, we've already solved this problem, or something very much like it, for our gravitational orbits. For our gravitational orbits, recall for the for an orbiting planet, we had the equation of motion. So it was mr double dot was going to be equal to, there was a minus, and it was gmm over r squared r hat, where we wrote the gmm of g times m as k. And so these two expressions are nearly identical. So these are nearly identical. The only differences are a negative sign and just some constants, right? So instead of something involving gravitational constants and a product of masses, we have a Coulomb's constant and a product of charges. Okay, so much of the work we did for the gravitational case can be reused for the Rutherford scattering problem. So this is one of the, in my opinion, one of the times when you get to see some of the beauty of physics, because we solved a problem where we were thinking about things on astronomical scales, right? The sun and the planets in the solar system. And now we're going to use the same analysis that we had for that problem, and we're going to apply it to the scattering of elementary particles, or an alpha, like interaction between nuclei. So now we're going from astronomical scales down to some of the smallest scales that we could imagine. So the analysis of r double dot, right, we would write the vector r as its magnitude times r hat. We'd take a time derivative. We would have to remember that the r hat changes its direction, and so its derivative is not equal to 0. And then we would do another derivative, and all of this would lead to, let's see, m r double dot minus r theta dot squared is equal to ke q over r squared. This is exactly what we had for the gravity case, except for the constants involved and the negative sign. And the other thing we would find would be conservation of angular momentum, where little l is the angular momentum divided by the mass of, in this case, our alpha particle. From here, what we would do, so instead of redoing all of this, we would define u as 1 over r. We would make that substitution. We would write r as 1 over u. We would take two derivatives, and we would have to use chain rule. We would recognize that if r depends on theta, so does u. And so we would use chain rule when we take time derivatives of u as a function of theta. And we would repeat everything we did, and we would come to an expression that looks like this. And so I encourage you to do this and just verify for yourself that it all works. It's a good way to review the analysis that we did in the last case of gravitationally interacting masses. Okay, so then recall what we did is we could divide by the mass, and we could divide by u squared, and what we would end up with, and let's divide by a negative sign. So I think we're going to divide by minus mu squared. So if we did that, we should get an L squared d2u d theta 2 plus ul squared is equal to minus keqq. The u squared goes away and we divide by m. Okay, in fact, what I should have done is I should have divided by also an L squared. So let's do that. And we'll just stick in an L squared over here. Okay, so d2u d theta 2 is equal to minus u plus keqq over m L squared. This looks like the harmonic oscillator. Again, this is exactly what we did last time. So we could say W is defined to be U plus KEQQ ML squared, and we would find that d2u d theta 2 is the same thing as d2w d theta 2, because when we take the derivative, the u plus a constant, the constant will vanish, and we'll get this is equal to minus w, and our solution would be w is equal to some amplitude cos theta minus theta naught. Okay, so it's like the harmonic oscillator, remember, except the harmonic oscillator had a x double dot was equal to minus k over m times x, and the solution to that was x was equal to a cos, and then it was some omega naught t minus a phase factor where omega naught was equal to the root of k over m. The only difference is that the coefficient in front of our w is a 1 instead of a k over m, and so instead of root k over m multiplying t, we get a root 1 multiplying theta, which is just theta. All right. So then we could say, well, u is w minus kqq over ml squared. So that is 1 over, u is also 1 over r, and so it's w, which is this a cos theta minus theta naught, and then minus kqq over ml squared. And then inverting everything, r as a function of theta can be written as a cos theta minus theta naught minus keqq over ml squared. Or we could write this as ml squared over kqq is equal to minus 1 plus a m l squared kqq cos theta minus theta naught. So this is the radius, or the distance from our helium nucleus, distance from let's write it this way: the distance from the gold nucleus to the alpha particle as a function of theta. Okay, now just like last time, we have two integration constants, a and theta naught. And so what we're going to do is we're going to try to figure out if we could come up with an interpretation of what these different constants represent. So let's go back to this picture where we've got our our gold nucleus over here, and then we've got our alpha particle initially over here, and then it follows this path like so. I think I want to see if I can do a little bit of a better one. Okay, and then let's say our alpha particle right now is not so far away, but it's coming in, and at some instant, this is the distance between the two particles, and here is theta. So one thing I'd like to think about is, when is r as small as it can possibly be? So we want to think about when r here is a minimum. In the numerator is just a bunch of constants. -1 is a constant, plus the coefficient of the cosine is just a bunch of constants. The only thing that can change is this cosine function. And cosine goes between -1 and +1. R can't be negative, so it must be that cos theta never goes negative, right? Otherwise, we'd have in the denominator a -1 minus something, and so we'd get a negative distance, which doesn't make sense. So it must be that the cosine is always positive, and the biggest it could possibly be is 1. And so when the cosine is equal to 1, that makes the denominator a maximum, which minimizes r. So r is a minimum when the cosine function, which is cos theta minus theta naught, is equal to 1. Well, cosine is equal to 1 when theta minus theta naught is equal to 0, or theta is equal to theta naught. Okay, so if we look at this picture, r minimum is this distance of closest approach, and so it's something like this. This is r minimum, and theta naught represents that angle right here. So this angle is theta naught. Okay, so that's fine. Let's return to an intermediate step. One of the intermediate steps was an expression for u is 1 over r, this thing. So I'm going to rewrite this expression. So we return to u is equal to 1 over r is equal to a cos theta minus theta naught, and then we had a minus Coulomb's constant, product of charges, over ml squared. Okay. Let's draw this picture one more time. Well, at least one more time. We might do it more than that, actually. So there's the gold nucleus, and our impact factor B is this distance. And then what we're going to do is we're going to have our alpha particle scatter, something like this, and we were going to extrapolate back here, And one of the things we were looking for was this scattering angle. Okay. And so what I want to think about is, when is R really large? When does R go to infinity? So for example, our alpha particle, it started out here, far away, when, let's say it started way off to the left, and in that case, R is equal to infinity. And so at some other time, maybe our alpha particle is sitting over here, and we measured some angle theta. But then at some different earlier time, our alpha particle was over here, and we had some other theta, blue one. And at some other earlier time, our alpha particle was over here, and we had some other angle, the green theta. And so you can see that as our R gets longer and longer as we move the alpha particle away, the angle theta shrinks. And if you take that to an extreme limit where R is infinitely long, an infinite distance between our alpha particle and our gold nucleus, theta would go to 0. So R goes to infinity when theta is equal to 0. So when R goes to infinity, that corresponds to U as 1 over R goes to 0. So we could go over to this expression, and we could say U is equal to 0 when theta is equal to 0. Okay, so U is equal to 0 when we have A cos theta minus theta naught just becomes minus theta naught, and then we have minus K QQ over ML squared. Cosine's an even function, so cos of minus theta naught is the same as cos of theta naught, and therefore A, if we solve for A, what would we get? We would get KEQQ over ML squared cos of theta naught. And we know that theta naught represents the angle when we have the shortest possible distance between our alpha particle and our gold nucleus. So is there any other time when R goes to infinity? Well, after the alpha particle scatters from the gold nucleus, it goes off in some direction. And, if you just wait long enough, it will be an infinite distance away again. And so the question is, what is the angle when R goes to infinity after the scattering? So there is another R goes to infinity solution when theta is not 0. And so let's find that solution. So we require 0 is 1 over R, so 1 over infinity is 0. So this is U is A cos of theta minus theta naught minus KQ over ML squared. But we just found an expression for A, so we're going to take this expression for A, and we're going to sub it into here and see what that leads to. Okay, So we're going to end up with what? K Q Q ml squared cos theta naught times cos of theta minus theta naught is equal to, let's bring the other term to the other side, KEQQ ml squared. I should put a little subscript, that's Coulomb's constant. And so cancel, 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 cancel. Okay, so that's nice. Therefore, the condition for r goes to infinity is cos theta minus theta naught is equal to cos of theta naught. There's two possible solutions. Two possible solutions. One is that theta is equal to 0, which we've already considered. That's the one that we use to write an expression for A. The other way that we could make the equality hold is that we set theta equal to 2 theta naught. Okay, because then we'd have cos of 2 theta naught minus theta naught, which is cos of theta naught. Okay, so what that means is, if we draw the picture one more time, maybe I'll give myself a little more room. So here's our gold nucleus. And then our alpha particle comes from over here. And this is our impact parameter B. And it comes and it scatters away like so. Let's try that again. Okay, maybe one more time. One more time I'm going to try this. Okay, let's go with this one. And so we were extrapolating back from here, and we said that what would happen is we were going to be looking for the scattering angle theta. And now this angle here is 2 times theta naught. This is 2 theta naught, because when we set r equal to infinity, then what we're finding is the angle between horizontal and a line that goes out to where the particle ends up when it's an infinite distance away. And what this picture shows us is that 2 theta naught plus the scattering angle is equal to 180 degrees, or pi radians. And therefore, we could say that theta naught is pi minus theta s over 2, or alternatively, if you wanted to solve for the scattering angle, that would be pi minus 2 theta naught. Okay, but in an experiment, what you could actually measure is theta s. So once theta s has been determined experimentally, we can calculate theta naught as pi minus theta s over 2. And this parameter a, which was one of our integration constants, is determined by theta naught. So once we know theta naught, we could calculate A in the following way. Or, if you remember, one of the quantities that was in our expression was ml squared A k times q was equal to, so that was one of the quantities we had. Now we've determined that that's equal to 1 over cos of theta naught. So let's scroll back and let's remember this A ml squared k q. Here was our solution for r, the distance between our alpha particle and the gold nucleus as a function of theta. And the quantity that we just calculated was A ml squared over k q. And we found out that that was 1 over cos of theta naught. So if we rewrite this expression for r, we end up with r is equal to ml squared over k q divided by -1 plus cos theta minus theta naught over cos theta naught. So this is the distance between alpha particle and gold nucleus as a function of theta. And you know, really what I want to emphasize once again is that most of the hard work was already done because we analyzed a completely different problem, the interaction between two massive objects. But a lot of that analysis translated directly to what seems like a completely independent problem. So what we did in this video was we spent most of our time just determining the integration constants and their meaning, theta naught and A. But the analysis, the hard work, was already done. So before I stop this video, what I did is I plotted the position of our alpha particle for a bunch of different angles. And so how could you do that? Well, if you were to set your gold nucleus at a position of 0, 0, and so we could make a, say, a y-axis here and an x-axis here, and your alpha particle is going to come along and scatter, and let's suppose that it was at some intermediate position over here. This is r and this is theta, and so this is your alpha particle, and so you would say that its xy position is equal to, well, what? R cos theta is, this is r cos theta, and over here is r sine of theta. So at the position that I've drawn, the alpha particle is at a negative x position, so its x position is minus r cos theta, and its y position is r sine theta, but we just calculated r as a function of theta. And so if you pick some values for the constants in the numerator, which is essentially like picking a certain value for the angular momentum L, and you pick a theta naught, which is the angle of closest approach, then you can just plot the xy coordinates for different values of theta. Okay, and so I made those plots. and I want to show them to you. And if you go to the course website, you can take a look at them there as well. So here's an XY coordinate system. I've placed the single circular point is the gold nucleus position. And here is a plot for the alpha particle position when the distance of closest approach is pi/6. And so that's a relatively small angle. And so that means that the scattering is quite strong. And in fact, the alpha particle comes in and it gets deflected, not straight back, but it doesn't go very far into, like, it never goes to positive values of x. Okay, so all I'm going to do is I'm going to make the exact same plots, but I'm going to change the theta naught value. So here's theta naught is pi/4. And so this angle between the horizontal and the position of closest approach, so here, this is now pi/4, or 45 degrees. And for this case, what we find is that the alpha particle comes in and it scatters almost vertically up. And so here's pi/3. So this is the angle in here is pi/3. And the last one I do, I think, is 2 pi/6. 2 pi/5. Okay, and so it's kind of a neat problem where we were able to use a lot of the, we're able to use a lot of the analysis that we had already completed about kind of astronomical scale objects and apply it to nuclear scale objects. All right, perfect. So that's it for today. Thanks very much, and we'll talk to you next time.